Right, check this out. Benzoin condensation. Benzoin condensation is when an aromatic aldehyde or a ketone is present where condensation is taking place for benzene based aldehydes and ketones. For example, if I take 2 moles of benzaldehyde, react with Cn minus or NaCN, you would get this product known as benzoin. So how does this occur? So first on benzaldehyde, cyanide Cn minus will attack as a nucleophile. You would get this you'll get this intermediate. And this is very interesting. This O minus will take this H plus. So there is an intramolecular proton transfer here. As it happens, you'll get this as C minus. By the way, why it is happening? That C minus could be stabilized with this cyanide form. Okay. Not just that, it can get stabilized with phenyl also. So there is an extended conjugation here that's keep this anion stable. And next, once you get this anion, it can be used as a nucleophile to attack on the second molecule. As it occurs, you will see this addition would take place, and internally again an intramolecular transfer takes place. Okay, again one more time, you will see IMPT happens, and you will get this as O minus and OH here. And it realizes that cyanide is a good leaving group now. So O minus will push the electrons and cyanide will be relieved. That's how you will get this product as benzoin. Typically, how the questions are asked is if benzoin is been, benzaldehyde is been treated with KCN, what is the product? If further oxidation, what is the product? Okay. So you can see first X is formed here, which is a benzoin. And on further oxidation with PCC, you will get this as keto form. By chance, if there is an alkyl aldehyde and then you react with KCN, so you will get this as O minus and CN, which is a regular nucleophilic addition. And thereafter, there is no carb anion forming here. Okay. Instead, O minus will take H plus and convert that into cyanohydrin. So that's the difference. For alkyl group, you will get cyanohydrin. For aryl groups, you will get this as condensation products. So this condensation product, which you call it as benzoin. Okay. So typically, this is how it works. The next type of mechanism, okay, which is asked, the next type of name reaction which is asked is Favorowski reaction or Favorowski rearrangement. Okay. The condition here is when we have alpha haloketone, alpha haloketone that is treated with base like OH minus, OR minus, NH3 and amine derivatives. This gives carboxylic acids or esters, okay, or amides. How does this work? Let me show you one reaction here. So pH, CH2, C double bond O, CH2Cl. So alpha halo is must. And then suppose if at all I treat this with NaOH followed by hydrolysis, then you would notice that this will get into CHPH2, another PH2 and C double bond OH. See the mechanism here. We have pH, CH2, C double bond O, CH2Cl, and OH minus will go and extract this proton from alpha position. You will get this as pH, CH minus, C double bond O, CH2Cl. Internally, as a nucleophile, SN2 type of a reaction would happen, intramolecular SN2 type of reaction. Now, notice we will get a 3-membered ring with a ketone here and this has phenyl group here, and this has, that's it. Only this is the intermediate which has been formed. Okay, and once you get this intermediate, because it's a three-member ring, it is highly unstable form. So OH minus will go attack on this carbon, correct? And it will open on the direction where the carb anion is more stable. So you would notice we will get this as double bond O and OH, and we will get this as pH and minus. Okay, so we'll get this as pH and minus. Now this on hydrolysis will convert into double bond O, OH, and here this will be pH. So that is the product formation, correct? So this is the evidence that has been identified that there is a OH minus which is formed. I mean, there is a three-member ring which has been formed. So you would notice that this is resonance stabilized. So major form. So this is the major intermediate which is formed. The other side, the attack would be minor, correct? This is what would happen. Okay. Let me share one example here. For example, in case if you have double bond O and Cl here. Imagine I'm treating first with CH3NH2. Okay, so that will create a carb anion here at this position. Cl is here, and then internally the attack would happen. Cl minus will go away. You will get a three-membered ring like this, double bond O, and here this five-membered ring would be present. And thereafter we will get this as OH minus, and this OH minus will attack here. The bond will break here. That will convert into five-membered ring like this with minus charge here and double bond O, OH here, correct? And this, by chance, if the reaction is given after this, the reaction is given uh, as CH3, sorry, ETO minus. Furthermore, the reaction is given as ETO minus and ETOH. Okay, ETO minus and ETOH. So in that case, we will get ester form in the acid here. So H will come here and double bond O, OET will form here. So this is how the ester formation is observed. So it all depends upon what is forming and what place. Okay, done. So this is the reaction that is going to happen using Favorsky rearrangement. Next, let's understand what is Perkin's reaction. Next, let's see what is Perkin's reaction. Okay. Well, you see, Perkin is also a cross-aldol condensation between an aromatic aldehyde and an acidic anhydride. Okay. And here you can notice an aromatic aldehyde and an acidic anhydride in the presence of acetate salt. That will give you the product which is cinnamic acid. Cinnamic acid. Well, how do we get that? Notice one by one the mechanism here. So we will have CH3COO minus been treated with HCH2 C double bond O, O C double bond O CH3, which is an anhydride. So this CO minus will take H plus. This will maintain an equilibrium to get CH3 COOH plus CH2 minus and C double bond O, O C double bond O CH3. This is an anion which is coming from an anhydride. So now I have a benzaldehyde PHC double bond OH which will react with this CH2 minus C double bond O, and O C double bond O CH3. So this C minus will attack here, open the bond here. So as it happens, you will see, as it happens, we can see that pH CO minus, and we'll have this H here connected with CH2, C double bond O, O, C double bond O, CH3 here. Okay, this is what is going to be formed. Now, if I write this in a particular oriented structure wise here, you can see pH, then we have CH, O minus here, okay, and then we have a CH2, and then a C double bond O here connected to an oxygen, which is connected to another C double bond O and a methyl here, like this. So that makes this O minus to attack internally this way and form a six-membered ring. We'll have this as pH, CH, O connected with C with O minus, connected with another oxygen, connected with carbon, this way with double bond O. So this is that six-membered intermediate which is forming. Okay. So now this O minus will push the electron here. As soon as this push, this CO minus will be opened up. Got it? So I'll take this here. And as soon as that open up here, so you can see we'll get this as pH, CH. We have this as, O with C, double bond O, CH3. And here we have COO minus. And here we have CO minus. Correct? So once you get this here, on heating, you would notice that ester pyrolysis will happen, because you can see this is alpha and this is beta position. So we can notice that ester pyrolysis will make this as a double bond form here. So we can get this as pH, double bond CH, COO minus plus CH3 COO H, COOH. Correct? Now this on hydrolysis, will convert into pH, CH double bond CH, COOH. So this is a final product formation. Correct? So this is a mechanism where we are able to see an aromatic aldehyde is connected with an anhydride form. So wherever you see this case, an aromatic anhydride, you'll always use this. You can always make this product. See, what is a minimum requirement? That there should be at least two hydrogens present here, because one is utilized here. Second one, when the uh, ester pyrolysis is happening at these 2 points. Got it? So minimum two is required. So let me show you one example. What if I have something like benzaldehyde here, CHO, and react with, uh, pH, CH2, C double bond O, O, C double bond O, okay, CH2pH, and that is been treated with pH, CH2, COO minus, and heat. So the shortcut is very simple. You remove this oxygen and these two hydrogens as water and join them both. That's it. So now I'll have this as benzene with aldehyde, which is CH double bond C. One will be pH, the other one will be COOH. The one more group will be pH CH2 COOH. So this is the product form. Yeah? Guess this is clear. Done with Perkins reaction. Please check. Done, right? Everybody? Right. Now, let's discuss about the next reaction, which is Canizarose reaction. Canizarose reaction is where we have disproportionation redox reaction happening. Okay. And there must be between same aldehydes. In fact, you can have two different aldehydes also, but usually disproportionation between same aldehydes is what is observed. That's why we call it as a disproportionation. It involves a hydride shift. There must not have any alpha hydrogen. These are the basic conditions that we should have. Okay. The next important condition is high high base concentration. Okay, as much as 50% NaOH or KOH, like this. Very high concentration of base should be utilized. Got it? Now let me show you example how it happens. See, let me start with an example. Suppose if I take 2 moles of HCHO, okay, if I take 2 moles of HCHO, react this with 50% of NaOH concentration. Then 1 mole will convert into a salt form, the other will convert into an alcohol form. Now, if you notice, an aldehyde structurally, it will have, you know, zero oxidation state here, while as a part of a acid, now it has +2 oxidation state here, and as a part of an alcohol here, it has -1 oxidation state. Okay, in fact, -2 oxidation state. Correct. So you can see from 0 to +2, there is an oxidation happening. From here to here, there is an oxidation happening. And from here to here, there is a reduction happening. So this is oxidation. This is reduction. Okay. See how the mechanism drives here. So first I have HC double bond OH treated with OH minus. OH minus being a strong nucleophile will attack here, convert this to O minus H and OH. Okay. Now this is where things get more interesting. If you have HC, O minus, H and OH here, O minus is a strong donating group. O minus is a strong donating group. So it would realize this fact that it is a strong donating group. So it will try to attack the next molecule here. So by pushing these electrons here and hydrate getting shifted internally. And this carbon hydrogen bond breaking is, difficult. So it will be a slow process, and that is the rate determining step. Hence it will become HC double bond O, okay, OH plus C, I got one hydrogen attached here, so C O minus H and H. And this compound, internally, it will take H plus from here, and what we report the final product as HCOO minus and CH3OH. So this is the final product. And these are the steps that are involved. Okay. So I'll write some quick examples here. So examples, if you notice. So if you have 2 moles of PHCHO and we have 50% of NaOH, correct? So we'll get this as PHCOO minus Na plus and PHCH2OH. Likewise, if you have 2 moles of Pivel aldehyde, this is called Pivel aldehyde. I'll have 50% NaOH, making this into COO minus, and the other one will make it CH2OH. Got it? This is how the mechanism and reaction is driven. Okay. Now, if you go back, what is the rate of the reaction here? Rate of the reaction, because it depends upon 2 moles of aldehyde and 1 mole of OH minus. So this is the rate, and order of the reaction is 3. Okay. Now, because the rate determining step, hydrogen is been moving out, so rate of hydrogen will be greater than deuterium, greater than tritium. Okay. Suppose if concentration of NaOH is above 70%. Okay, just a minute. Hello. Sorry. If concentration of NaOH is 70%, okay, sorry, is above 50%, then what will happen? See, these steps are same. Up to these steps are same. But one step that changes here is the intermediate which we had, HCO minus and OH, and we had H here. This will further react with OH minus and take this H plus, sorry, take this H plus and convert this into HCO minus, O minus and H. So this is a dianion radical form. Earlier what we got here is, mono anion radical form. So this is monoanion. Now we have dianion. Okay. Dianion is very good in terms of donating nature, because you can see here it is very good in terms of donating nature, because you can observe here that this has donating groups from both ends. So here also it is donating, here also it is donating. So it is electron donating group from here, electron donating group from. Since it is better electron donating group, now the reaction would happen slightly faster. So which means the next step will be HCO minus, O minus and H as reacted with HC double bond OH. So you will notice this H minus will move here as this closes, and this bond will open up, and that will make it HCOO minus, and here you'll get CH3O minus. Okay, this is the rate determining step now. If this is the rate determining step, what is the rate of the reaction now? Rate of the reaction will be equal to some constant into aldehyde square and OH minus square, because there are 2 moles of OH minus that were utilized. Okay, so order of the reaction here now, order of the reaction is 4. Okay, so what is the important conclusion here is that in case of rate of hydride shift, rate of hydride shift, if you compare, then HCO minus and OH and H, this would be lesser than HCO minus, O minus and H, because here hydride shift is much easier. Okay. In fact, if I compare them in this part also, that is HCO minus and OH, and here we have hydrogen, and here we have HO minus and O minus, and deuterium also, still this is more. Likewise, if you have any group PHC, O minus, OH and H, if I compare that with benzene with OCH3, because OCH3 will be better donating group, so this will be better hydride shift cases. Okay, so these are the hydride shift cases, everybody. So I hope all of you understood how the Cannizzaro works. Now, notice the application. First one is intramolecular Cannizzaro. That means internally, this one between CHO and CHO, one will convert into acid part, one will convert into an alcohol part. So simple mechanism is the same earlier how we did that. That is the same type of mechanism, just internal. Okay. So because if you compare the rate here, we have CHO, CHO and CHO minus and OH. And then there is a hydride shift here. Internally, there is a hydride shift here. And due to that hydride shift, here we'll get CH2OH and bottom carbon will become CO minus. Correct. So rate now is dependent on only one aldehyde. So one aldehyde power 1 and OH minus here. Correct. Okay. So because we have both the aldehydes equally present, so we can say this will take 2 moles of that OH minus during the mechanism, and order of the reaction in this case will be 3. Okay. See what I'm trying to say. Let me show you. C double bond OH is there, and we have C H O minus, OH and O minus, OH and O minus is there. Okay. So again, you will react this with OH minus just to make sure that this H plus will also go away, so that internal transfer happens easily. So we'll get this O minus, and that's when this pushes internally, this H minus will go, and thus making the upper carbon as CH2O minus and the lower carbon as COO minus. Okay, and that on hydrolysis will convert into CH2OH and COOH. So that's how you can have 2 moles of OH minus observed here. Done. So this is about intramolecular Cannizzaro reaction. Next one is about cross Cannizzaro, which means between two uh, different aldehydes. Okay, correct. So how do we compare here is that between these two, whichever is more reactive towards nucleophilic addition reaction. For example, in this case, aldehyde is more reactive, formaldehyde is more reactive than benzaldehyde. The one which is more reactive will be converted into the acid part, and the one which is less reactive will be converted into the alcohol part. That's the easy way to remember. Okay, correct. Check out. Here we have between these two, benzaldehyde is less reactive, so that will convert into an alcohol, and nitrobenzaldehyde is more reactive, so that will convert into acid. Similarly, here benzaldehyde will convert into acid, and since here more donating groups are there, it is less reactive, which makes this as alcohol, CH2OH. Next one, nitro group will become acid, and this will become alcohol. Okay. You can notice this one, NO2, methyl and OCH3, which is better donor. I just told you that. Whichever is better donating groups we have, that is better donor. This will be better donor, but the reaction will always happen more on the more reactive NAR, nucleophilic addition reaction case. Then next, in case if you have this OD minus, check out which will get migrated from here. Okay, so first I have HC double bond OD here and HC double bond OD here. So basically, you would notice that this hydride is the one which will shift here during the mechanism. So what is the product I will get? I will get this as DCOO minus and CH2DOH, correct? Similarly, in the next case also, only D is migrated, so it will become DCOO minus, and you'll have this as CD3OH. And next, here, first this will convert into a keto form, that is PHC double bond OCHO after hydrolysis. Then Canizero would be applied. So as you react with OH minus, pH, this will become an alcohol part and this will become an acid part. Same way here also, this will become an acid part and one of its mole will become alcohol part, like this. Furfural is the same thing. This is called furfural. It will become CO minus and one mole will become alcohol. Done. These are all the cases what you need to know how to work out on Canizero. Finished? Done. You guys, any doubt? See, cross Canizero, their applications. Now, let me just take one applications of, Canizero reaction here. So the application, one of the application is benzyl benzylic rearrangement, which is just similar to Canizero form. This is benzyl, okay? So if you have P double bond O, PH, this is what we call it as benzyl. Benzyl, when you react with concentrated OH minus, you will get this benzylic ion, and that's why it is called benzylic rearrangement. So check out the mechanism. It is very similar to Canizero. So we have pH, C double bond O, C double bond O, pH. As OH minus reacts, it will go and attack on one of the carbons here. Then it will form pH, C double bond O, C, O minus. We have pH and OH. And now, as this O minus will try to close, this pH minus will shift internally. So it is very similar to the intramolecular Canizero, where phenyl is shifted in this case. So we'll get this as O minus and pH, C double bond O, OH. Again, IMPT, intramolecular proton transfer will take place to get pH, OH, pH and COO minus. So that is benzyl. From benzyl, it is converting into benzylic form. Okay. See one example here. Suppose if at all I have two benzene rings like this with double bond O and double bond O here. And then I'm treating this with concentrated OH minus. Okay. So now we'll get the same thing here. First, OH minus would be attacking on this position, open up the bond. So we will get this as, okay, we'll get this as O minus and OH. Now, as soon as this double bond closes, this benzene will go attack here from this end. So that's how we will get, that's how we will get this benzene. And here, then we'll get this 5-member ring. And here we'll get this as O minus and COOH. Again, internal transfer will take place. And then we'll get this as OH and CO minus. Okay. So this is a product form. So ring got compressed here. The product is the same. You can see same as the above case. Benzyl benzylic rearrangement, how it happened. Okay. Please check. If you have any doubt, you can ask me. Next, check out Tollens reaction. We take an aldehyde, take one more aldehyde, making it a cross kind of aldol or a canizero to get this kind of product. Okay, these two products. In this reaction, we will see the first 3 steps are aldol and the last step would be canizero. Okay, let me show you the mechanism one by one. So first, you can notice CH3CHO, as you react with OH minus, this OH minus will create an enolate ion here first. So you'll get CH2 minus and CHO. And that when you react with HCHO, HC double bond of H here. So this minus will go attack here. So this is a typical aldol reaction. So we will get this as CH2OH or O minus. That will connect with CH2CHO. Okay, CH2CHO. And one second. Right, sorry. So this on hydrolysis here, so we'll convert into CH2OH and then we have CH2CHO. And this compound, again when you react with OH minus, it will take away H plus, takes away H plus, and you'll get this as CH2OH and CH minus CHO. React this with second mole, make it as a cross aldol again. So this C minus will attack here, getting this into CH2O minus. I'll directly write the OH step here with hydrolysis. And now we have CH, already we have CH2OH and CHO, correct? And this compound, again, it has one more hydrogen, So we react with OH minus. Same thing would happen. It'll extract H plus from here. So we'll get this as CH2. So what do we have here? Basically, we have C minus, which is connected to CH2OH and CH2OH and CHO. This when you react with HC double bond of H, again C minus will go connect here. That will give us CH2OH, CH2OH connected to carbon, which also has CH2OH, also has CH2OH and CHO. Okay. So basically, how does it look like? It looks like this. So we have OH, OH, and OH with CHO. So this is what has been coming across. Now you can notice that there is no more alpha, there is no more alpha hydrogen. And since there is no more alpha hydrogen, OH minus will go attack on aldehyde this time, making it as a Cannizzaro form. Okay. So as it goes here, so you will get this as OH. Okay. Sorry. Okay. My mistake. Because now, if you have HCHO to react, HC double bond of H to react. Now OH minus notices that HCHO is more reactive than this one. So this time OH minus will go attack here. And you'll get this as O minus. So is this one OH, OH, and OH. Here we'll have this as CH, sorry, C double bond OH, okay, plus HCO minus, OH, and H. So as this closes, now this H minus will go attack on this carbon. This is a Cannizzaro step. And doing that, now we'll get this compound. So we get this as OH, 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 and OH, and this will convert into HCO minus. Okay, so this is how you will get the final product. Okay, look more like swastik form with HCO minus. So notice this, we have 4 moles of aldehyde. So we get this form and HCO minus. Please check. I'll give you 2 minutes. Check out the entire mechanism. If you have any problem, let me know. I'll also write it down. The first step. This is first aldol. This is the second aldol. This is the third aldol. And the last one is Cannizzaro. So these are the 4 steps that are happening. Please go through it once quickly. Okay. So a lot of time this would be used as an application. After the I mean, let me show you the application as an example here. For example, it will be asked like, CH3 CHO is used with HCHO in excess. Okay, first using basic medium. So when this is coming, the first product what you write is this form. Okay, so this was the type of form. So this is the first product you will get. Now listen up. In case if it is being treated again with 2 moles of CH3 CHO. Okay, or let's say I will take this as uh, cyclohexanone, 2 moles of cyclohexanone in the presence of H plus. Okay, in the presence of H plus. Now what does this mean? You know that when you have a dry HCl, these two are the two OH groups, I mean diol type of a groups here, that will give you acetal formation, and that's exactly what happens here. So I will have, this ketone here having a this double bond will convert into, right, so this double bond will convert into connection here with 2 oxygens here like this, and connected. So this is how It's connected. And the second mole will be connected to the next carbon here like this. The, this is the final product form. Okay. So a lot of questions could be asked. What is the degree of unsaturation? 1, 2, 3, 4. So there are 4 degree of unsaturations. Are how many number of oxygen compounds are present in the final product? This one, or whether this will give you Tollens test, or whether this can react with lithium aluminum hydride or not. Because this is an acetal form, it does not react with any of that. Okay, so important application, guys. Please check. By the way, this was already asked in JEE Advanced exam, I think 2023, I guess. Same product. Okay. Right. Now, let's take one more reaction here known as Tischenko's reaction. Tischenko's reaction is also an application very similar to Canizero, where the reagent we use is trialkoxy aluminum. And here there is a disproportionation of aldehydes into esters. Basically, if I take 2 moles of aldehyde R CH2CHO. Why I'm taking this one particularly is it doesn't matter whether you have an alpha hydrogen or not. Okay, with or without alpha hydrogen, still you'll get the same product. So that is AlOET thrice. So this would make into a ester form, that is CH2 C double bond O O CH2R. This is the ester form what you will get. Now imagine if this undergoes Canizero. So if it undergoes Canizero, what is the product? I'll get this as RCH2 COOH. One will form into acid, the other one will form into alcohol. Correct? Now imagine as if you are making an esterification of this acid and alcohol. That's it. That's the easy way to remember. Got it? Okay. So Tischenko reaction is all about making these aldehydes into acid form. Cool. I hope this part is clear. Right. So these are main reactions regarding Canizero. Okay. Now, notice one thing. If you are testing aldehydes and ketones, correct? That means either I'll be testing the carbonyl group, that is whether there is a presence of aldehyde or ketone or not. That can be done by 2,4-DNP test. We have learned this, what is 2,4-DNP earlier. We can use sodium bisulfate test, which will give white PPT. We can use iodoform test in case if there is any methyl group present. So I can use the iodoform test if in case of there is any methyl group present. Okay. So this way you can identify aldehydes and ketones. But what if I want to distinguish only aldehydes and ketones? Okay. I'm not identifying aldehydes and ketones, but I want to differentiate between aldehydes and ketones. Okay. Because all these three tests will give, positive for aldehydes as well as ketones. But what if I want to differentiate aldehydes and ketones? Then we will be using Tollens test, Fehling's test, Benedict test, and Schiff test. Okay, these are the 4 tests that you will be conducting to identify the difference between aldehydes and ketones. So Tollens test is oxidizing the aldehyde into acids and reducing a silver salt into silver mirror. So if a silver is reduced in the form of a white PPT across the test tube, that would be a silver mirror form, that is called as the Tollens test. Benedict test is converting aldehydes to acids and using copper sulfate solution here, you would be getting a red PPT, brick red PPT of Cu2O. Failing is also same with using copper sulfate. You'll get a brick red precipitate. Only here there are 2 different solutions we'll be adding before the reaction. One is Benedict A, which is copper sulfate solution, and Benedict B, which is sodium or potassium citrate salt. Here, failing solution, which is copper sulfate, and failing B which is Rochelle salt. Rochelle salt is sodium potassium tartarate. Okay, I'm just giving a very basic briefing here to understand how to differentiate these three. Okay, and the last one is shift test. Shift test is if you convert acid aldehydes to acids, and there is a pink coloration observed here during the reaction, and the component which you'll use is para rose aniline hydrogen chloride, which get decolorized on passing SO2. What exactly is that? I'll show you with equations, don't worry. But this is the overview of making the aldehydes and ketones to be distinguished using these four tests: Tollens, Benedict, Failing, and Shift test. Okay. Normally, if you have a molecular formula C3H6O, I could imagine like an aldehyde or a ketone or an alcohol. Of course, you can have an ether also, but ethers are non-reactive, so I'm not using that. So, in case if it is 2,4-DNP, aldehydes will give positive, ketones will give positive, and alcohols will not give any test. Tollens test. Tollens aldehydes will give positive. They will not give positive on ketones. They will not give positive on alcohols. NaIO, that is iodoform. Iodoform, here it is not observed. Here it is observed. Here it is not observed. Sodium metal is presence of strong polarized hydrogen, which is there in alcohols. Okay, got it? I guess this idea is clear now. Now, before going into further details, correct? So first, we will visit back to Tollens test. What is happening in Tollens test? Let me show you one by one here. Tollens test. So we take ammonical silver nitrate as the reagent. So first, take AgNO3, add NaOH. On adding NaOH, we'll get a brown color PPT, which is Ag2O. And then add aqueous ammonium solution. Then it will become a clear solution because it will convert into an complex form. So this is the complex form which you will get. Okay, and this is a complex form which you will get. Now notice the oxidation state of aldehyde, guys. Aldehyde in this case possess oxidation state +1. After it becomes an acid, it will have +3. So the number of electrons transferred are 2. So which means I require 2 moles of silver ions to get precipitated. So 2 moles of silver will get precipitated during the reaction. So for every 1 mole of aldehyde to get oxidized, 2 moles of silver has to get reduced. Okay. So the overall reaction would be like this. Okay. So the overall reaction would be aldehyde RCHO plus 2 moles of AgNH3 twice plus 3 moles of OH minus, that will give us RCOO minus plus 2 moles of silver plus 4 moles of ammonia. This is the overall reaction that happens. Clear? So this is Tollens test or Tollens reagent, how it, happens to change. Got it? Now, before coming into these cases, first, let me give you a briefing on failing and Benedict solution also. And then I'll come back and visit there. Okay. So what are all the cases that we need to check out? Okay. 1 second. Sorry. Check. Now let's talk about mm, failing solution. Failing solution and reaction. How does this happen? Overall reaction is like this, where you have an aldehyde reacting with copper 2 plus complex. I'll show you what is a complex also. So I need to take 2 moles here, 2 moles here, and this will convert into 2 moles of R COO minus, and this will convert into Cu2O, a brick red precipitate. But how many moles of base will be consumed to do this? We'll have 5 moles of OH minus consumed. Okay. Now, what is this complex exactly? See, solution 1 or solution A. Failing solution A is aqueous copper sulfate. Solution B. Solution B here is sodium potassium tartarate. Sodium potassium tartarate. Sodium potassium tartarate. Sodium potassium tartarate has one more name, which is Rochelle's salt. It's also called as Rochelle salt. How is the structure like? See, Rochelle salt will be COO minus, then we have CHOH, CHOH, and COO minus. This is Rochelle. This is if I connect this with sodium on one end and potassium on one end, this will become sodium potassium tartarate. Now, as you treat this with copper sulfate, 2 moles, it will convert into a complex form. So that is Cu connected with 4 bonds with 4 oxygens here, this way. So these are the same oxygens which are connected on the tartaric acid. You get CO minus and CO minus and CO minus. So you can notice that copper will get a coordination number of 4 here. So it is this complex which reacts with this aldehyde to eventually convert into CO2O, a brick red precipitate. Okay. So Failings and Benedict will have everything same except the uh, s- um, except the solution B. Solution B is slightly different from different from different for what do you say Benedict solution. Okay. Okay. Let me show you. So in case of Benedict solution, Benedict solution will have, okay, Benedict solution A, okay, and Benedict solution B. So A is copper sulfate and B is sodium potassium citrate. Sodium potassium citrate. So how will be the structure of this one? It will be like COO minus, CO minus, CO minus. Okay. Usually sodium citrate is been taken. Potassium combination is not essential here. So simply I'll write down sodium citrate salt. This one with OH. This is that solution B. Okay. So here this will also going to form a complex, and that complex will also give you the overall reaction like this. So let me write the overall reaction here also. RCHO plus 2 moles of Cu2 plus 5 moles of OH minus. That would give us RCO minus plus Cu2O, a brick red precipitate plus 3 moles of H2O. Right? So this is the overall reaction. I suppose this is clear, everybody. Okay. Now, before going into the above list, first I want you to realize in which case what will happen. Okay. So, what is the important condition here is for for Benedict and failing solution, Benedict and failing solution, okay, alpha hydrogen is must condition for aldehydes. So when we are talking about the oxidation of aldehydes, alpha hydrogen must be present. So therefore, if you have benzaldehyde or if you have glyoxol, okay, they will give you negative test with failing solution or failings reagent or Benedict reagent. Okay, so both will give you negative test. Got it? Failings and Benedict will give negative test. Second is first point. Second point is since failing solution or Benedict reagent or Tollens reagent all are basic solutions. You must have seen the overall reaction there. Base is used. Basic solutions. Then hemiacetals are unstable. Hemiacetals are unstable and give positive and give positive test and give positive test. For example, if you have R, CH, OH and some OCH3, this is a hemiacetal. This is hemiacetal. And if this hemiacetal is being treated in basic medium, you know that it will be unstable and convert back into an aldehyde plus alcohol. So now it becomes an aldehyde and alcohol. In that case, if you take Tollens reagent or Fehling's reagent or Fehling's reagent or Benedict reagent, they all will give positive test. Positive test as in it will convert into RCO minus. So any hemiacetal can give, but the hemiacetal after basic hydrolysis should only give you aldehyde and not ketone. So which means not all hemiacetal can give. For example, if you have this R and then we have OH and OCH3. This is also we regard it as hemiacetal. But with OH minus, it will convert into a keto form. And since it is keto form with Tollens, Fehling's or Benedict reagent, this will be negative test. Lastly, if you have an acetal, acetals are highly stable in uh, basic medium. It will not break also. So since they do not change into anything, if I take Tollens, Fehling's and Benedict reactions, nothing will happen. So negative test here also. This will be negative test as well. Okay. So important pointers. So please check in which case it will become positive or in case it will become negative. Okay. Next, another point, what you will notice is that in case of formic, in case of formic derivatives, that is, even if you have formaldehyde, formic acid, or formic chloride, all of them will easily convert into, I mean, they get oxidized into CO2 here. Okay. In this case, first, for example, here, this will convert into HCOO minus. And this HCO minus will get further oxidized to convert into CO2. Okay. So therefore, in the presence of Tollens, Fehling's or Benedict solution, this will oxidize into CO2. So all of them will give positive tests. So these all three will give positive Tollens, Fehling's and Benedict test. Will give positive test. Next, in case of oximes, sorry, hydroxylamines. In case of hydroxylamines, that is, if you have RNHOH, this will get easily oxidized to convert into RN double bond O. So this will give positive test with Tollens, Fehling's and Benedict. So in case of hydroxylamine, this is what you'll get. Next, in case of alpha hydroxyketones, it will get oxidized to convert into diketone here, like this, diketone. So this will also give you positive test with Tollens, Fehling's and Benedict. Okay, correct. This will also be positive test with Tollens, Fehling's and Benedict. Next, in case of terminal alkynes, so what do I get? RC triple bond CH. If you treat with Tollens reagent, that is silver ammonium salt, in that case it will convert into RC triple bond C minus and Ag plus, which is white PPT. This is a white PPT form. And in case of failing solution or Benedict solution, where you have uh, Cu2 plus here, correct? So that will convert into Rc triple bond C twice copper. So this will be, brick red color again, brick red coloration. So this is also going to give you positive test. Got it? Now listen, in case of carbohydrates, in case of carbohydrates, carbohydrates starting with glucose. See, glucose exhibits in a cyclic structure. Going ahead, we'll learn that this is a cyclic structure of glucose. This is how the cyclic structure of glucose looks like, where you have OH, 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 and OH. This is the cyclic structure of glucose. And similarly, we can have cyclic structure of fructose also. This one. So here we'll have OH, 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 and OH. This is cyclic structure of fructose. Cyclic structure of fructose. Here we have OH this way and OH here. So notice one thing here. In the first case also, in glucose also, this is a hemiacetal bond. Check out, this is a hemiacetal bond. Here also, this is an hemiacetal bond. So glucose, fructose, both will have hemiacetal bonds. And you know that hemiacetal bonds in basic medium, they will again hydrolyze, convert into aldehydes. Okay, in fact, fructose will also convert into alpha hydroxy ketone. And you know that alpha hydroxy ketones is giving positive charge. positive test. So both fructose and glucose will give you positive test here. So therefore, all monosaccharides, monosaccharides means the sugars which cannot be further hydrolyzed, like glucose, fructose, mannose, galactose, galactose, lactose, sorry, ribose, galactose, ribose, ribose give positive Tollens, Fehling's, and Benedict test. Okay, hence they are called. Hence they are called. That means all these sugars are called reducing sugars. They are called reducing sugars because they will reduce silver, they'll silver salt or copper salt from Tollens, Fehling's, or Benedict. Okay, so all of them will give positive test. Everybody. Okay, glucose, fructose, mannose, galactose, ribose, and so. Okay, so if it comes to sucrose, right? Sucrose is a combination of these two structures, that is glucose and fructose structure. And the structure of sucrose looks like this here, and it is connected with here like this OH. Here we have OH, OH, and OH. Okay, this way, and H here. Okay, so here we have H. Sorry, here also earlier I have to write H here. Here. So here we have OH, 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 and OH. So this is how the sucrose structure looks like. Now notice in sucrose structure, this is OCO. That means there is no hemiacetal bond. This is only acetal bond. Acetal bond only. Since there is an acetal bond only, so sucrose is a non-reducing sugar. Non-reducing sugar gives negative test with Tollens, Fehlings, and Benedict. Okay, this is what you will observe with sugars, everybody. In fact, more detail about sugars and more reactions of that will anyway learn in biomolecules. For now, this is how much information you need to know it about Fehlings, uh, Tollens, and Benedict solution. Okay. Now coming back to this here. So when it comes to Tollens test, what are all the products? I'll write down quickly. Check out in this case. First case, I'll have HCHO will convert into HCO minus plus silver. Here CO2 and silver. Here CH3 CO minus and silver. Here benzaldehyde will be PHCO minus and silver precipitate. And here double bonds will not be disturbed during this reduction. They are mild oxidizing agents. And then here we'll have CO minus and CO minus and silver. Next, we have pH, double bond O, double bond O, and here R and double bond O. Here it is hemiacetal, so RCO minus and ROH like this, plus silver will get reduced. Okay, okay. Okay. So I have written it here. You can see this is open structure of glucose, fructose, mannose. All of them will give you the same product here. So they'll all give you going to give positive. Sorry. Right. This also I will told you that also I told you here it will be correct. So C triple bond C minus silver plus this is the white PPT here, correct? So if in case of terminal alkynes, okay. See, all compounds will give you positive test for Fehling's and Benedict except for 4 and 6. Okay. And in case of Fehling's test, you'll get a red PPT like this. Now, what is shift test? Check out shift test here. Shift test is when you have this particular compound, which we call it as para rose aniline. Okay. So first para rose aniline is being added to aldehyde. And so that will give you a pink coloration. Okay. So how is that pink coloration? What is the product? Let me write down that. Okay. So for example, if I take an aldehyde RCHO, okay, then first it will convert into RCOO minus. And this pink coloration is because of this complex which I'm writing right now. So which is, uh, by the way, that is the same thing I'm writing it here. Okay. But see how it changes to small structural features. So here we'll have NH with S, double bond O, double bond O, CH, OH, R. Okay, CH, OH, R. And here I'll get double bond connected with this benzene like this and with double bond NH2 plus. Because of this non-benzenoid structure only, we will have that color formation. So NH, S, double bond O, double bond O, and CH, OH, and R. Okay. This is how the aldehyde will get added to the sulfur side, which gives the color. Okay. And eventually from here it get oxidized to RCO minus. Convert into RCO minus. Okay. So I think the shift test is clear. Now, shift test will give positive with, benzaldehyde also. So that means gives gives positive test with benzaldehyde and glyoxal. Unlike Fehling's and Benedict, this will still give you positive test with these two. Okay. So guys, this is the list of oxidizing agents and their detailing and some working about how things will go. Now, I want to put a complete table so that when you do the revision part, it becomes very easy for you to come and check. Okay. So first, let me take one by one, which are all the cases, compounds. I'll put it like a table here. Right. See in this list, what are all the compounds we can make? First, this is compound. Okay. So this is the test. Okay. So that is Tollens test. Tollens. This is Failings or Benedict. Okay. So starting with first R CHO. Positive, positive. Okay. pH CHO. Positive, negative. Got it? CHO CHO. CHO CHO. Negative, positive, negative. Okay. And RCOR, ketone. Negative, negative, negative. Ketones, both of them are negative. Okay. Hydroxyketone, that is RCHOH and C double bond OR. So this is positive, positive. Okay, I'll do one thing. I'll remove one line here. Yeah, check now. Sorry. Please check. If you have CHO and COOH, in that case also this is positive, this is negative. Got it? If you have R C triple bond CH, this is positive, positive. Okay. And if you have hemiacetal RH, OH and OMe, positive, positive. In case if you have RH, OMe and OMe, that is acetal, negative, negative. In both cases, it will be negative. Okay. If you have RNHOH, hydroxylamine, positive, positive. Correct. Next. Now, this is interesting. In case if you have hydroquinol, OH and OH, OH and OH, hydroquinol. Okay. So, in that case, this is positive in cold condition. This is positive in hot condition. Okay. Positive and hot condition. Next, you can see glucose. Write down this as glucose, fructose, mannose. They all will be positive and positive. Okay. Next, in case if you have OH, OH, and OH, if you have three OH groups, this is called fluoroglucinol. This is called fluoroglucinol. This fluoroglucinol. Fluoroglucinol will also give positive and positive test here. Okay. Clear? Next, resercinol. That is, if you have OH and OH, this is resercinol. This will give positive and positive test in hot condition. Okay, right. So this list will help you recall whenever you want to just have a quick look at all the compounds which can give positive test or negative test. You can quickly go through it once. Guys, clear? So this is about the oxidation using Tollens, Valence, and Benedict solution. Next oxidation reaction. Next oxidation reaction is about Bayer-Villiger oxidation. Okay, Bayer, Bayer, Bayer-Villiger oxidation. Okay, right. So, well, what is Bayer-Villiger oxidation? Let's see. Bayer-Villiger oxidation is about using, any aldehydes or ketones. Suppose if you have any aldehydes, okay, and we simply use a peroxy acid, okay, peroxy acid, we will end up getting an ester. Okay. Okay. So check. So how does the mechanism work? What is the reaction here? Let me show you mechanism. So suppose if you have pH C double bond O CH3, okay, and you have HOO C double bond O CH3. This is a peroxy acid. Some peroxy acid you can take. And let's say this is an isotopic oxygen. Okay. I'll write this as oxygen 18. So if this oxygen, which is a localized electron, will act like a nucleophile and add on to it. So what do we get on doing that? We will get this as pH, then we have C. We will get this as OH connected with this oxygen O, which is connected with next oxygen, which is connected with C double bond O and CH3. And here we have CH3. Okay. So this is the intermediate what you will get. Now, when you know that oxygen bond is very weak. Okay. So this will try to break onto this oxygen side here. As it does, the lone pair from here will try to push to make it into C double bond O. That's when between methyl and phenyl, one of the group will migrate to this oxygen. This is that same 18 oxygen. And as it does, you will see we will get this as PH O C double bond OH plus and CH3 plus CH3 COO minus. And this CO minus will take H plus from here. And that's how we'll get the product as PHO C double bond O CH3 plus CH3 COOH. That's how we'll get the esters. Okay. So mechanism is simple. We just have to get this migration done. Now it all depends upon which will migrate. That's the whole point here. Okay. One of them will migrate. And here this is the 18 one, oxygen 18 one here. Okay. So migrating aptitude or migrating behavior. Okay. Migrating aptitude. Okay. In Bayer-Villiger oxidation, if you compare, the first would be H minus, then it is 3-degree alkyl group, 3-degree alkyl, then it is 2-degree alkyl. Very interesting here. So 2-degree alkyl, then comes phenyl, everybody. So within phenyl we have electron donating groups, then only phenyl, then phenyl with electron withdrawing groups, and then comes 1-degree alkyl halide. So 1-degree alkyl halide, then comes CH3 minus, and last comes R C double bond O minus here. Okay. this one. So this is a group that can migrate. So this is a very different order than the regular ones. Okay, so you just have to follow that. Okay. Yeah, this is what you need to check it out. So let me show you with examples here. For example, if you have R C double bond O C double bond O, this is the first exceptional one where if you have anything like R dash COOOH here, and this is, let's say, isotopic oxygen, and then you will get the oxygen between these two carbons. This is the exceptional one. This is the exceptional one. Okay. Rest, if you have any other case, right? So notice this one. If you have like this double bond O and methyl, and then I'm taking this as PH CO3H. So then you will notice that ester would be forming here because the migration would be much better between these two positions. Right? So basically this side the migrating aptitude is more because this side you have 2 degree, this side we have 1 degree carbon. Alright? So that is a product what you will get. Similarly, if you have ketone here and if I treat with, you know, MCPBA is meta chloroperoxybenzoic acid. So that will give you ester on this end. 1, 2, 3. This is the major product form. Okay, clear? So similarly, if you have C double bond O and we have, sorry, C double bond O, and then we have phenyl on the other end. We learned that 2 degree will make a better migrating aptitude. So if you react with MCPBA, you would get this as O, C double bond O. So that will make it phenyl here. So this is the major product. Clear? So I hope you got an idea what is the Bayer vinegar oxidation here. So simple thing, you just need to mainly focus on the uh, migrating aptitude, guys. Okay, and the last oxidation reaction, everybody, oxidation reaction of SCO2, selenium dioxide. Okay, selenium dioxide, what does it do? If you take any aldehyde or a ketone and you treat this with selenium dioxide in acidic medium or acidic uh, mild acidic conditions, you will get the alpha position to get oxidized like this. So what do we get is glyoxal. So glyoxal. Similarly, if you have CH3, CH2, CHO, okay, and SCO2 with ACOH, okay, CH3, C double bond O, double bond O, H. So this is methyl glyoxal. Correct. In case if you have, this way, so you have two different sides of alpha, right? So you should always go for more stable enol form. Which side more stable enol will be? Right hand side. So this is a major product that you will report. Okay. So mechanism is simple here. See, if it comes to mechanism, so that is SeO2 plus H2O. It will first show an acidic form, which we call it as selenous acid. This is selenous acid. So it is the selenous acid which makes the reaction here. So see, that is CH3, COH, let's say double bond CH and CH3. This is the enol form which I have written, correct? So on this enol form, uh, if it is reacted with OH and selenium with another OH and double bond O, if you have this way. So this is how you can expect to remove, water from here. So you will get a minus charge on this position here, correct? So you'll get this minus charge which can be pushed to make a double bond, and from this carbon it will connect on to oxygen and pushing this bond to selenium. Okay, so this is how the reaction takes place, and that will give us CH3, C double bond O, and CH3. This is connected to oxygen with selenium and one OH group still present on it. Okay. So now this is what would happen. This oxygen will try to convert into a double bond form here, where this H minus will take away with OH and selenium will get reduced. Thus, we will get this as CH3, C double bond O, C double bond O, and CH3 plus selenium will get reduced. So guys, this is the overall reaction, how it works with selenium. Honestly, mechanism is not important for you guys. You just need to know how the reaction works here. Okay. Let me show one very important example that, that is very commonly asked in exams. So suppose if you have a ketone here and I treat this with selenium dioxide. Okay. So first you would get a diketone here like this. And can you notice this is very similar benzyl benzalic case. That's why when you react with NaOH, first you will get a 5-membered ring here like this, because it will become more like benzyl benzalic form with OH and COO minus. And that when you hydrolyze it, you will get acidic hydrolysis. You will get this as OH and COOH. This is very standard question. Okay. Right, guys, I hope you understood what are all the reactions here. This is using selenium dioxide form. Yeah. So this is all you need to know it from this particular topic. Okay. So I think we are done fair enough number of questions and mechanisms in this. Okay. Anyhow, in case if there was asked something like which cases Canizero can give and which cases Canizero can't give. So check this out. This I'll write it like an example. Cases where Canizero is not observed. Canizero is not observed. So first case, nitrogen with some methyl group here connected to benzene. Okay, C double bond OH. Although it is a benzaldehyde, still it will give no Canizero test. Even if you have OH also, no Canizero test is observed. Why is that? Because this group will become O minus and this is an extremely strong donating group. Here also is a very strong donating group. So for such strong donating groups, Canizero is not observed. Okay. Next, in case if you have 3-membered ring like this, 3-membered ring. So in case of 3-membered ring also, this will not give you, okay, with OH minus, you will find no aldol or no Canizero. No aldol, no Canizero. Okay, reaction type is different here. Next, in case if you have CCl3CHO, this one will also not give you any Canizero form. Okay, so by chance if you come across these cases, guys, so this will not give any Canizero test. Okay, one exception is this I told you already. Suppose if you have CH and CHO. Okay, next example, if you treat with this OH minus, okay, no aldol because of extreme crowding, extreme hindrance, but goes for Canizero, goes for Canizero, goes for Canizero reaction. Sleep properly. Okay, guys. Right. Okay. This is all you need to know, everybody.